Hello everyone, thank you for giving me this opportunity to introduce my research. Today I will bring AI generated media and security topic to you. Well, my name is Shu Hu. Currently, I'm an assistant professor from our department, our school. Yeah. But my office is in India. Okay, so let's look at these face images. So could you please let me know which one is real, which one is fake? Just a guess. Yeah, which one is real, which one is fake? Everything is fake. Yeah, good. Yeah, so it's very hard to identify, right? So I can let you know the answers. The images from the first rule are real images. The images from the second rule are fake images, right? Okay, so let's think about the generation first. So why do we need to consider the generation? There is a famous quote, "What I cannot correct, I do not understand," from Richard Feynman. So let's first review the generation from the past. I mean, the past means before 2019. So there is a famous model called autoencoder. So the autoencoder is famous at that time. This is the fundamental framework of the autoencoder. So there is the original face A, and we send this face to the encoder and to get the latent variable, latent features, and then send the latent features to the decoder A to get the reconstructed face A. And also we can send a face B to the encoder and to get the latent variable, and then send to the decoder B to reconstruct the face B, right? So this is the traditional pipeline of the autoencoder. But how can we utilize this autoencoder to generate a fake face? Well, we can send the face A to an encoder and to get the feature representation. And then we send this feature representation to the decoder B instead of the original decoder A, so that we can reconstruct the face B from A. So this is a very trivial pipeline to generate the fake face. Later, there is another famous model called generative AI. I believe you are very familiar with this model. And there are two networks. The first network is called the generator. The second network is called discriminator. And we generate the fake face images from the random noise. So the generation, what is the generation after 2019? Well, generation in the era of the generative AI. So from this figure, you can see lots of companies, lots of models are proposed to generate AI-generated content like images, videos, and audio, right? Also the text. Well, there are two famous models. The first one is called diffusion model. The second one is called multimodal large language model. Well, how can we use them to generate media? So let's look at the image first. So let's combine the prompt and the image and send them to an established model, for example, from the imaging 2, Stable Diffusion, Midjourney, DALL-E 2 or DALL-E 3, so that we can generate realistic images, right? Similarly, we can also generate videos. Same pipeline. So we send prompt and combine with the image and send them to the Pika or Stable Video Diffusion model so that we can generate this card video. How to generate audio? So we can start from the text and to generate the mail spectrogram. And after that, we can generate the audio. Okay, how about the multimodal? We can combine different modalities of the data, right? For example, the text data, video data, or image data, and send them to a foundation model. And after that, we use the large language model to do some modifications. For example, generate a cat, generate a dog, something like that, right? And after that, we send the features to the another foundation model for the decoder so that we can generate like this video combined with a description, text description. Okay, so maybe you are familiar with the Sora 2. Sora 2 is the latest model from OpenAI. So let's look at this video. Very good, right? Very realistic. Okay, I can stop here. So let's continue the presentation. Next, I want to highlight the detection. So there is another famous quote: every contact leaves a trace, from Edmond Locard. Why do we need to detect them, detect the AI-generated content? So we also call them deepfakes. So deepfakes can manipulate perceptions, poses a profound threat to the integrity of demographic process and individual reputations. Therefore, detecting deepfakes is essential to combat misinformation and maintaining society's trust in the information ecosystem. So this is the reason why we need to detect them. And of course, from this image, so starting from this year, I mean the beginning of this year, so there is a very famous misinformation on the social media. So it is the fake AI voice, and to mimic the real voice from the Michael Rubio. And the deepfakes, we have different modalities of the deepfakes. For example, the images, videos, and the audio. And let's look at this figure again. But now let's add the detection. So with the detection, so you can find it is like a cat and mouse game. Well, we have lots of detection tools are proposed in the academia, in the industry. So, for example, the detect GPT from the Stanford University, and also AI face dataset from my lab. Directions in detection. So what we can do for detection? So we have different directions, not the future directions, the current directions in this domain. Let's look at the image first. We split it into pure detection and beyond detection. So what does this mean? So we can just detect them if it is fake or real, right? We can also find another attributions about the detection result. For example, the interpretability, right? Like explain why it is real, why it is fake, right? And for other modalities, for video, audio, multimode, we also have pure detection methods are proposed and beyond detection methods are proposed. But today, I would like to highlight the fairness challenges in this domain. So let's look at the traditional deepfake detection framework. Well, we send the original images to a detector, but we use the whole features from that image. And after that, we can get the real and the fake, right? And recent years, many researchers focus on how to improve the generalization capability of the model, of the detectors. And so that you can find there are two terms, intra-domain testing and cross-domain testing. Intra-domain testing means the training set and the test set are from the same domain. Cross-domain means they are from different domains. So why do we need to care about the fairness? Let's look at this result. The misclassification rate of female black is greater than the misclassification rate of male white, so that the attackers prefer to generate fake faces with female black, right? Okay, there is a baseline. So we proposed this method, the first method in 2023. So at that time, I'm trying to combine the traditional fair learning approaches from the machine learning domain to the deepfake detection, so that the method is very trivial. So we only add a fairness loss into the learning objective and to guide the model training. So we can preserve the fairness within intra-domain testing, but cannot maintain the fairness in cross-domain testing. Well, let's think about why. So at that time, I identified two reasons. The first reason is from this theorem. The theorem demonstrates that if the original feature X is entangled with the ground truth label like a fake or real, Y, and the demographic labels or demographic features, D, so that we cannot train a fair model with the theoretical guarantee. The second reason is that when we train the models, let's check the loss landscapes. And from this figure, you can see we have lots of like local minimums, and there is only one global minimum, but it's very hard to achieve that goal. So we proposed a new method. It is called the preserving fairness generalization in deepfake detection. And this paper is accepted by CVPR conference last year. And the idea is also very trivial. So we split the original features into two parts: domain agnostic forgery features and the demographic features. After that, we combine them. So it is like we break the connections between the forgery features and the demographic features so that they are not entangled, right? And after that, we combine these two features to send to the detector. But we also use the fair learning approach to guide the model training. However, we add another module called flattening loss landscape to flatten loss landscape so that we can guide model to achieve the global optimal. And based on the results, we get the intra-domain fair and the cross-domain fair. So this is the whole framework. The framework contains three modules. The first module is called distinguishment learning module. The second module is the fair learning module. The third module is optimization module to flatten loss landscape. Okay, so from the experimental results, you can see our method outperforms the other baselines on different datasets with different backbones. And if we print the breadcam visualization results, so you can find our method targets the face region instead of the background region. Well, after that, I'm thinking, so we faced a challenge during that time. The challenge is that we are trying to find lots of datasets can help us to prove our method works, right? So we are trying to find the AI generated image, video with demographic labels. However, we cannot find any existing on just one very small dataset. So that this motivates us to propose this new dataset, to build this new dataset. It is called AI-based dataset. And the paper is accepted by CVPR conference this year. Well, in this dataset, we first collect the AI-generated images and the diffusion model-generated images and the deepfake videos. After that, we clean the dataset, we filter the dataset to extract the face region. So next step, we need to assign labels to them, right? So we designed a framework to predict the labels. For the first skin tone label, we extract the face region and to use the k-means clustering method algorithm to find the top 3 colors within that face region. So we use the top 1 color and to merge it with our reference. For example, here we have 10 tones here. So we can find a specific tone very similar to the top 1 color, so that this method can be used to generate the skin tone label, right? For other labels, for example, for the gender label, for the age label, we leverage the foundation model CLIP, and we design a classifier building on the CLIP model. And the method is very easy. So for example, for the classifier, so you can just use the three-layer multi-layer perceptron, so that it's very easy to train because we leverage a very powerful foundation model here, CLIP. Compare our dataset with other datasets. So you can find our dataset contains a lot of AI generated images from different generative models. And also, we provide 3 different types of the labels: gender, skin tone, age. So in that work, we also do a benchmark study. We evaluate 12 detectors from 4 categories. The first category is the backbone. The second category is based on the frequency-based method. For example, Leverage utilize the single label artifacts to do the detection. And the spectral method just use very advanced architecture. And the fairness enhanced model, like I presented before, we proposed a method in 23 and a method last year, right? So from this table, we can find all detectors trained with our AFS dataset can achieve over 98% AUC. And also, if we check the fairness scores, we find a lot of models cannot get a very fair performance. Instead, except our proposed fairness enhanced method. So this is the good thing, right? Because most of the models trained with our dataset can achieve very good performance. But when we test those models, those trained models on new dataset, on thin datasets, for example, the CCV2 gene data, we find the performance cannot be maintained, like the utility fairness cannot be maintained. Why? So we identified a very challenge in the dataset because we design models to predict the labels, right? So it's very easy to generate a noisy label. For example, like this face. The real label is female, right? Based on the features. But in the dataset, it is mislabeled as male. When we train the models with noisy data, so you can find the performance is decreased. Well, after that, this year, we published another work in ICML conference. And in that work, we are trying to preserve the fairness under the noisy labels. And we also provide theoretical guarantees, but I omit lots of details here. After that, I'm thinking another question. Can we improve utility, fairness, and generalization without demographic labels? Because when we need to train these fair models, we have to use the demographic labels, right? But can we just train them without demographic labels so that we do not need to care about the issue of the noisy label, right? Well, this motivates to explore another work. We find another definition of the fairness in the fairness domain called individual fairness. The original the original principle of the individual fairness says, okay, similar individuals should get the similar outputs. Like these 2 dogs, if we send these 2 dogs to the classifier to get the predictions, so we can find the probability, the predicted probabilities are very close. For example, 0.9, 0.8. However, this principle doesn't hold in defect detection. Why? Because if we check these 2 faces, right, and these 2 faces are very similar, but the labels are totally different. One is fake, one is real. So if we send these 2 images, face images to the classifier, so we can get the probabilities like 0.9 for the fake, 0.01 for the real, right? So this method, this principle, individual fairness principle, doesn't hold in defect detection. So this is the formulation of the individual fairness. A trivial solution is that because we consider the similarity between faces, right? So if we remove the thematic regions, not the thematic regions, I mean the thematic features, and convert them to the frequency domain so that we can remove the similarity within the semantic feature, right? And we are trying to train a detector based on the frequency domain features. But the method doesn't work. So you can see the distance between fake and real is less than the distance between the real and the real. So we expect to see the distance between the fake and real is greater than the real and the real, right? So that the principle of the individual fairness can hold. Well, we proposed a method. So we break the semantic features like relationships, and we use the patch shuffle. After that, we extract the artifacts based on the delousing. And after that, we convert them to the frequency domain feature. So you can see the now fake and real distance is greater than the real and the real, right? Based on this motivation, we designed the framework here. The framework is very easy. So we modify the original feature and do the patch shuffle and to extract the residuals and then to convert them to the frequency domain and to design this new individual loss formulation. But in the meantime, to improve the generalization capability of the model, we leverage the anchor learning method, but you do not need to worry about the details about it. It is very trivial. And you can find lots of papers discuss this anchor learning. And this paper is accepted by the SAM Multimedia Conference this year. So in the experiments, when we compare the baseline models, like original model with the original individual fairness learning, and the naive model, so we can find our method outperforms the baselines. And we also adapt our method to the existing advanced deepfake detectors. And you can see we can further improve their performance in terms of utility and fairness. Well, there is a question. Was this work done by a PhD student? In fact, the first author is a high school student, and the third author is also a high school student from Carmel High School. So what I want to deliver is anything is possible. Well, this year, we organized a very famous competition in this field, in the machine learning field. And this competition is accepted by the European conference, very selective. And the competition is in December. And the competition is about the fairness in AI face detection. We received lots of teams, registered teams around the world, like 64 registered teams, 158 participants, 33 organizations from 20 countries. So which means this topic is very hot and most people like this topic. So I'm thinking, what is the future of this competition? So now I'm applying for organizing this the third competition. And I'm trying to submit a proposal to CVPR conference. Hopefully we can get it accepted. And after that, next year, we will go to Denver to organize the second competition. And we will include more tasks. So in the first competition, we only include the fairness competition, fairness task. But we will include other tasks. For example, deploy the models to the mobile device and to just improve the generalization capability of the model, right? To compare the generalization performance. And we get, until now, we get 2 sponsors. One of the sponsors is Qualcomm. Okay, this summer, our group developed a platform. So this platform is called SenseGuard platform. So we are trying to integrate all the detectors into our platform. And it is free to use. Everyone can access this platform. And the fundamental difference between our platform and the existing platforms is that we integrate the large language models into the platform so that you can ask questions. Okay, so for the traditional detectors, we provide 13 detectors here, and everyone can upload a media, image, video, or audio, and select a corresponding model to get the performance, like how many percentage for the real prediction or for the fake prediction. And for the large language models, we developed this module, and everyone can upload an image and to ask a question, is it fake or real? Why it is fake or why it is real? It's very trivial, right? And very useful to get the answers. What are the future directions? So today, I only highlight the fairness challenges, but there are many challenges in this domain. For example, the attribution. How can we find a specific model to generate these deepfakes, right? And generalization, of course, a long challenge, right? A long time challenge. So the model, if we deploy the model to the real world, and can we maintain the performance like 99% accuracy, 98% accuracy, right? And the interpretability. So can we get the explanations for the detection result, like a real or fake? And the localization, we localize which region is manipulated. And the robustness. So if we add the adversarial attacks to the original image, can the performance maintained? And the empirical study. So we evaluate the current detectors and to see what are their limitations and what are their challenges. Okay, let's revisit the Sora 2 video again. So previously, you may think the Sora 2 generated video is more realistic, more real, right? However, I can let you know there are lots of artifacts in the video. So if we go to this frame and let's look at the eyes, so you can find the specular highlights are totally different. So maybe you can check your friend's eyes and to see these two specular highlights and to see if they are consistent or inconsistent. Basically, for the real people, the specular highlights are consistent. So, but from this frame, it's very clear to see they are inconsistent, right? This is the second frame. And if you check the pupil shape, and so you can find the pupil shape is irregular. So we should expect to see the circle, right? But not. This is the third one. Third one is very crazy. So irregular pupil shapes and inconsistent specular highlights. And when I saw these eyes, I think I do not need to buy the Halloween decor. So we can just print these images, right, as the Halloween decor. By the way, happy Halloween. So advertisement time. So next semester, I will offer a new course. This course called Applied Generative AI in Mobile Computing. And we will cover several concepts here, like before generation, generative AI. So we will explore the deep neural networks on the image, on the structured data, and later we will cover the generative AI models, for example, diffusion models, GAN models, and version autoencoder. And we will also explore the security. So for example, responsibility, trustworthy of the generative AI. And for students, if you would like to explore more opportunities in this course, for example, beyond the project, and I will recommend you to the Qualcomm because Qualcomm is the sponsor for this course. And Qualcomm very glad to have more students to explore how to deploy the AI models, generative AI models into their mobile device, like IoT device or the laptops or the phones. This is our lab. So our lab is machine learning and media forensics lab. We published two papers, two books this year, and many publications. If you check my publication record, you will see lots of publications. And most of them accepted by the published on CVPR conference, ICML, AAI, IGCAI, SMMM, Journal of Machine Learning Research, AMI, and multimedia, transaction on multimedia. And we are fortunately covered by major outlets, and for example, the Science magazine. And our sponsors include Encode, Qualcomm, NSF, and Purdue University, and Indot. And we we are working on different modalities of the data: text data, video data, audio data, image data, text data. And we are working on robust machine learning and also the applications on AI-generated content detection and the medical image analysis. We developed two platforms, as I'm showing you before, right? So the first platform is SenseCloud platform. The second platform is a chatbot for medical image. And we have lots of team members from the lab, starting from the K-12 and to the PhD students. And we really welcome you to apply for our lab and to get more research opportunities and explorations. Thank you. Thank you so much for your attention. Any questions? Yeah. Yeah, good question. So in the fairness domain, there are three categories: the pre-processing and the in-processing and the post-processing. So pre-processing means we modify the data to mitigate the bias, right? And for the in-processing means we train the models, we add specific loss functions to guide the model training to assist the model to get the fair, right? And the post-processing means we get the outputs, but after that, we design a small module to let the result become fair, right? Results become fair. Yeah. So, but in my group, we are focusing on the in processing. So, which means we design specific loss function to guide the model training. But yeah, of course, as you said, lots of researchers for the on the large language models, on the research on the image research, they prefer to use the pre-processing or the post-processing. Of course, we can also explore that those directions. Yeah. Thank you. Any questions?
Hi, Shu.
Yeah.
What's the accuracy of your fake prediction? I guess
Yeah, good question. So it's very hard to say well what is the exact number for the accuracy because it depends on the test domain, test data, right, and also your training data. So for example, in the current days, so maybe next week we will release the paper. So I collaborate with my colleagues from the political science department. So we are trying to evaluate the detectors, different detectors on the real world political effects. And we found that previously lots of methods say, okay, they can achieve 99% accuracy, 98%, 98% accuracy. And especially for the commercial tools, they also announce, okay, we can achieve 98% accuracy. But when we test on our real world political effects, we download them from the social media. And we find that the accuracy is just 60%. Yeah.
Yeah, that seems more realistic.
Yeah. Thank you. Yeah.
I joined late, so maybe you mentioned this before. I was wondering with the generated models, I have seen you only show images to people. Do you do like outdoor scene, and for example, like can you detect if it is a fake scene or not fake scene, or only with images with people, like people in it?
Yeah, as I mentioned before, there are lots of different modalities. For example, the like fake news, right? So the news contain the image part and the text part, and from our lab, because you know our lab is the multimedia lab or media lab. So now we are focusing on the image domain, but we also explore. We have a few unbudgeted students work on the video domain. And we also published a few papers on the to tackle the fake news detection. So we are working on the text detection. Yeah.
Do you say images? Which part of images?
General images, right? Yeah. So So now we are working on the face images, but as I mentioned before, we are working on political deepfake detection. So for that case, we are working on the general images. Yeah. Thank you. Any questions?
Sure,
Any
can you hear
questions
me?
from online? Yeah, go ahead.
Very good talk. But I came a little bit late, so I have two questions. So first is about the fairness. So to give an example that, maybe the female black, maybe, in the detection, you may get biased results, right?
Yeah.
But I think my question is, how can you guarantee the fairness across different categories? I mean, even some unknown categories, or you just test some known, some target, and to see if the fairness can be maintained, or if there's any way to guarantee that the fairness will be applied across different categories. That's my first question.
Yeah. Thank you for this question. So basically, when we train the model, we know the specific categories we should target, and we know the female male or the male black or male white, right? Something like that, so that we don't expect to see new categories in the test set. So this is the first assumption. And on the other hand, as you asked so how can we prove it is fair, right? So like this work, so we conduct a study, and we developed a method, and this method depends on the building on the robust machine learning, and this method in this paper we give proof as theoretical guarantee to say to show it is fair, because we have a definition of the fairness. So if we can achieve that goal, so based on the theoretical guarantees or the proofs, so that we can say, okay, so it has theoretical results or theoretical guarantee. Yeah.
So it's independent of the target, your categories, right? So say if it's if we're looking at something that not even human, it's not human, right? It's even animals or some, just a table, right? Or can we still guarantee that?
No, we are working on the inter-domain testing.
Okay.
Yeah.
Thank you.
Thank you.
So I have another question. So about the defenses or all the defenses that you just discussed. So I think theoretically we can apply those defenses for attack, right, to help attacker to improve. Is that possible? Right. So I see a lot of so for example that in your presentation that you pick up one page a frame from that video, right? So from the the light conditions or the difference from the eyes, we can identify the fake images, right? So if that's something significant, I wonder if the attacker can fix that. Right, and or to learn from your defense, and to improve their attack network, and to generate more, real images. Right. So I understand this is the mouse and the cat game, but so how that would go? So if the attacker can leverage the existing defenses, and how difficult it would be. Thank you.
Good question. Very good question. So, so when I was in 2020, I found these artifacts, and we published a paper in ICAPS conference. And after that, we received lots of attentions around the world. And the first time is that we find these artifacts in the GAN-generated images or videos. But after 1 year, it seems like most of the generative models integrate a module to fix these artifacts, like the new diffusion model generated audios, videos, or images. But nowadays, for example, today, we are looking at this Sora 2 generated video, but it seems like the artifacts are still there, right? Maybe they ignore these artifacts during the development, or maybe they don't think it is a problem, right? Because they want to generate the highly realistic video or image. And for the average people are very easy to trust these videos, right? So what I want to say, as you mentioned, it is a cat and mouse game. So we only expose these artifacts to the industry, to the academia, and we hope they can fix them, or they can use the software or post processing, something like that, right, to fix these issues. But we are still facing the we still find these artifacts in the real world. So I believe they can do better. For example, for the Sora 3, right? Maybe they fixed these artifacts, but I think it is still a problem there. For example, maybe very hard to fix or very easy to fix. Who knows, right?
Yeah, but for Sora, I think they may intentionally leave the market there because they're not, attacker, right? They're not malicious.
Yeah.
They want to generate videos, and they also want people know they're generated by their models, right? So but for malicious players here, right, they have the every intention to make it real, to make it to fool people thinking this is a real image or a video, right? So they may be more determined to implement the technical improvement. But yeah, I think that's one thing, but that's the intention, right? But on the other hand, from the technical point of view, how difficult it will be to apply those defense to improve attack. Is there's a tactical barrier prevent an attacker from doing that?
I believe this is not a big challenge. So, for example, they can just replace these two eyes from the real eyes, right? And it's very easy to fix, but they ignore this problem during the development.
Yeah. Okay. All right.
Yeah,
thank you.
Thank you. Any questions? Yeah. Good question. So, as I mentioned before, nowadays I'm working with colleagues from the political science, and we are working with. So, he collects a lot of political defects, real world political defects. I believe those defects are very hard to go through the detectors to get the real answers. Yeah.
Then can we think about what is some data characteristics, some inherent biases in the data, some inherent properties of the data that lead to certain kind of behavior, let's say bias or generation error, right? So can we pinpoint why that error occurs back to the data instead of along with focusing on the model? Right, so tying both instances together. Do you think there is any value in doing that?
Yeah, of course. So it is worth to explore the pre-processing method. So when we do the work in 23 for, as I mentioned before, there is the baseline, right? So we proposed that method, but we use the in-processing method to achieve the fairness. But at the beginning, we are trying to use the pre-processing to remove the data from the dataset the whole data set. But we face a few challenges. For example, if we are trying to build a balanced data, right? If we remove some of them, we will lose the information, right? So if we add a few new samples into the dataset, we will change the distribution of the dataset, right? So in that case, we are thinking maybe in processing is a better method. Yeah. Thank you. Yeah. Any questions? Okay. Thank you.